Okay, good afternoon, everyone. Welcome to this webinar titled From Dips to RocSlope, Integration and Beyond. My name is Grace Huang, and I'm the presenter for today. I am a geomechanics product manager at Rock Science. So the agenda is I'm going to show you two practical examples using both dips and RocSlope, how we can use them together to assess for slope hazards for two cases with different levels of available data. So perhaps a number of you are here because you're familiar with dips, whereas RocSlope was only released last year. So I'm going to provide a brief introduction to RocSlope before diving into the two examples. Now, throughout the presentation, feel free to post your questions in the chat. My colleague, Julian, will be monitoring the chat and collecting your questions, and we'll take Q&A breaks throughout to answer some of these live. For any questions that are unanswered in the webinar, we will also type up all responses and email them out within 2 weeks. The last note is please take a moment to fill out our poll questions, as we would really appreciate your feedback. So let's get started. First, what is RocSlope? We know that in rock slopes with hard rock mass and exhibiting jointing, the failures may occur through the defects that are weaker than the actual rock mass itself. So the program RocSlope would use real slope geometries and the mapped locations of the joints to find where blocks can form, which blocks can fail, using the 3D limit equilibrium method. And the failure modes considered are block sliding, lifting, and falling. And it would provide the factors of safety for every block if it's a deterministic analysis, and the probability of failure for the blocks if it's a probabilistic analysis. So because RocSlope utilizes real geometries, it can be used to analyze problems at different scales. So at the smallest scale, for instance, if you have a slope or bench cut, RocSlope can be used to analyze crest failures. If there are multiple benches, then the inter-ramp failures that are much larger in scale. And if the model is, for instance, this open pit, so at a much larger scale, then RocSlope can be used for a global hazard assessment, first determining where blocks can form on the slope, as shown on the upper right, and then providing a heat map of the probability of failure, as shown on the lower right here. So a little bit more on slope hazard assessment and what engineers care about. Realistically, blocks can only form where there are joints, and that these joints persist enough to intersect. And then among the blocks that can form, failures can only initiate in the daylighting and removable blocks. So RocSlope uses a realistic approach in the sense that it would use discrete and finite size joints to find these blocks and to calculate the block failures. So next is that engineers would like to know what are the mechanisms driving the failures. So in RocSlope, it can provide the forces, such as the external loading, water, whether it's the combination of low shear strength on the joints resulting in the failures, or it can identify key blocks. So the detachment of key blocks can lead to larger scale global failures. So as shown here, the green block is a key block because the detachment of this block can lead to the failure of this purple block behind the green block. So with the failure of the key block, we can get failure of a much larger section of the slope. Now, lastly, RocSlope can aid in the analysis of design and mitigation. It can identify the locations and magnitudes of support demands, and you can implement bolts, shotcrete, and the required support pressure within the program itself. Now, going back to the key blocks, if the key blocks are stabilized, then the slope is stabilized. So going back to the previous example, here, stabilize this green block also stabilizes this purple block. Okay. So in this sense, by identifying the key block, we can also understand the total true failure depth, and this quantity can be used to determine how much anchoring is needed to anchor into competent rock. So earlier, I mentioned that RocSlope uses discrete and finite joints. So how are joints defined in RocSlope? And there are three methods, starting with measure joints. So here, you can use measure joints if the orientation, such as dip and dip direction, are known, along with the locations X, Y, and Z, as well as the size. And in RocSlope, we assume that the joints are circular disks, where the center of the disks are defined by the X, Y, and Z coordinates, and the size of the disks are defined by the input for the radius, as shown here. Now, this grid you see is very similar to the grid data view that you find in Dips. And in fact, you can actually quickly import a Dips file, and the data will populate this grid in RocSlope immediately. Likewise, you can also import CSV files or any common text file types. The second method for defining joints is using synthetic joint sets. So here, you may not have as much data. You may have a couple of traverses, in which case you can then bring the traverse data into diffs, define the joint sets to analyze the set statistics for the distributions and orientation, size, and spacing of the joints. And then these distributions can then be brought into RocSlope, where you would first define a traverse for the synthetic joints, and then the disks or the joints would be populated along the traverse according to the input distributions. And again, we're assuming that the joints are circular. The last method to define joints is by importing a surface geometry of a common geometry file type, and then simply assigning joint strength properties to those surfaces. So for example, if you have the geometry of a fracture network, as shown here, then you can define different strength properties for the different joint sets making up the fracture network. So that was just a very brief introduction into RocSlope. So just moving on, now that I have introduced RocSlope and some of its basic integration with Dips, I would like to show two examples of how these two tools can be used in the basic geotechnical engineering workflow. So the workflow here is definitely not exhaustive, but typically the first step would start with field data collection. The data would be processed to analyze and then identify the hazards. The hazards can then be communicated, and if you know the consequences pertaining to the hazard, then we can communicate the risk. The workflow may stop here, or we can go on to mitigation and design, construction, and the ongoing monitoring of the performance. And if there are changes in conditions, we may want to reassess or revisit some of our assumptions, and this may prompt the need to collect more field data. So in my first example, my workflow starts with the detailed mapping of my slope geometry and joint orientations and locations. So today we have the technology such as LiDAR and photogrammetry to scan the most current slope geometry and to map the exact locations of the defects. Now, using all of this data, we would like to analyze the likely contribution of the map defects to slope instability. Now, for this example, I'm going to focus on the slope sections that are marked here with the dip and dip directions. So I'm going to jump into dips. So as a result of the field collection, I can now process my joint orientation data in Dips, right? So here I am in the grid data view in Dips, and I have close to 1,600 joint entries with values for the joint dip, dip direction, locations X, Y, and Z, and the observed joint length, which I've placed under the persistence column. And I have 2 additional entries for the strike and area. Now, for this data, I have a pole vector plot, and I'm going to define sets for my joints because I want to use the mean set data for kinematic assessment. And also the benefit of defining sets is that I would be able to obtain set statistics. All right, so quickly now, I'm going to define the sets. I've set 1, set 2. And to help you with defining sets, I would definitely turn on the contours. And now for my third set, you could say that this may be noise or it could be a set, but I'm going to treat it as a set in my example. So here. Okay. So once you have defined your sets, you can now go on to do a kinematic assessment. Typically, for kinematic assessment, we would examine all the various failure modes for planar sliding, wedge sliding, and toppling. But to correspond with RocSlope, I'm just going to limit my kinematic analysis to planar and wedge sliding with my slope dip of 70, general dip direction of 85, assuming a friction angle of 30, and a lateral limit. Okay, so you can see some critical percentages for planar sliding, and I'm going to toggle to wedge sliding. Right. Now here you see many intersections, but it may be more useful to view these intersections in terms of the mean set planes, or even set versus set planes, for example. Now, I would say that a kinematic assessment is really only a preliminary assessment because we have assumptions of infinite slope, infinite joints, no consideration for any external loadings or water pressures, which we know can have negative effects on our slope stability. So the unknowns at this point are where blocks can form in the real slope geometry and where the blocks are likely to fail. What are the size and volume distributions of the failing blocks? And if there are external loads and water pressures, what are their effects? So this is where I am going to go into RocSlope and take advantage of the fact that I have the real slope geometry and the map locations of defects to conduct a 3D block stability analysis. Okay, so this is my 3D model in RocSlope. Let me just briefly walk you through this. I have the model of an open pit mine, and you can see all the joints represented by circular discs, and you can see the various sizes of the joints. For this analysis, I'm assuming that the design factor of safety of 1. So this just means if the factor of safety calculated for a block is less than 1, it has failed. And I have successive failure enabled, which just means it can identify key blocks, if any. And I'm going to stick with a deterministic analysis in this example. So what are the components needed to construct this model? Let's take a look at the rock properties. Here, you would need the unit weight of the rock and any definition for the water surface. In this case, it's none. You would also need to define the joint strength properties. And here, I've just defined one using the Mohr Coulomb strength type, but you do have other constitutive models available. Okay. So we have our strength. Next is, how did I bring these joints into the model? So we have map joint data. So here I am using measure joints. So going into the define measure joints dialog. Okay, so what I did was I imported from the dips file directly, and the columns are populated automatically. You see we have a column for the dip direction, X, Y, Z locations, the radius. And in this case, my assumption is that the map length of the joints I would assign as the radius, or I should say the radius I assume to be equal to the map length of the joints. We also have a column for joint property. So this is the joint shear strength property. And I remember I used a Mohr Coulomb model. And I have 2 extra columns that are not being used. Now on OK, the program will basically populate these joints in the model according to the joint X, Y, Z locations and the radius to specify the size of the disks. Okay. Now, we are actually ready to compute. And just to give you a sense of the required compute time, I have close to 1,600 joints. And my 3D slope has about 40,000 tetrahedron mesh. And the compute took me about 3 minutes. So in the interest of time, I'm going to jump ahead to the results. Okay, so now you can see on the slope, we have some blocks. And the result set you're currently viewing are for the removable blocks. But let me change that to just the failed blocks, which are the ones calculated with a factor of safety less than the design factor of safety. Okay, so you can see that the result set has decreased because now we're only viewing the failed blocks. And the colors you're seeing on the blocks are the contoured factors of safety. So the first thing that jumps out at me regarding this result set is that the blocks that are formed are actually quite small. Now, when I go into the block information table to view the volume distribution, and I'm going to just double click on the volume header to sort the blocks from greatest volume to the smallest volume. Okay. I can see that my greatest block volume is 79 meters cubed, whereas the majority of blocks are actually less than 1 meter cubed, and some are as small as 0.02 or 0.1 meter cubed. Okay, so I would say in this case that these small blocks formed as a result of uncertainty in the joint sizes and persistence. So let's take a look at the distribution of the joint sizes, which we can do using both Dips and RocSlope. So in Dips, I'm going to just plot my persistence column, which is actually the map joint length. And this is quantitative data, and I'm going to filter the data by the different sets. Okay. So you see the distribution of the map's joint length for set 2. Okay. Some of the joint length are actually quite large, greater than 30 meters, but the bulk of them are actually down here, right? Less than 4 meters. And you'll find that this is also the case for the other set as well. Okay. Now, let's just view one of these joint sets in RocSlope. And I can do that by taking advantage of the filtering option in Dips, where I'm going to just filter out one of the sets, let's say set 3, add, and I can create a new file with just the grid data for set 3, and I can bring that grid data into RocSlope to view only that joint set, as I'm about to show you here. Okay. So what you're seeing now is the traces of the joints for one of the joint sets. And what's interesting is that you'll notice some of the traces when viewed individually are really quite small, but when viewed collectively with the other traces, you'll notice that they may actually belong to the same joint. So the implication here is that we may be underestimating the joint persistence or size, and that failures may actually occur not just through the joints, but through the rock mass itself through rock bridging. So RocSlope currently doesn't explicitly account for rock bridging. However, we can't analyze for the likelihood of a block forming through a sensitivity study of the joint sizes. So to change the joint sizes, you can simply go back to the measured joints grid dialog and use it very much like you would with an Excel spreadsheet. So for instance, currently I'm assuming that the radius of my joint disks are equal to the map length. But I can say, okay, I'm going to cut and copy my current map length to another column, and I want to use twice the original map length. And I'll apply the same formula for all of my joints. Okay. And just to summarize my sensitivity study here, here you're viewing the results for 3 different joint radius. Okay. Originally, I had 1 times the map length for the radius, but I also did 1.5 times and 2 times. You'll notice a trend in the increase in the number of blocks forming, but also an increase in the size of blocks that formed. So at this point, I would actually take a step back as to whether I trust these results or not. We can actually do a reality check against Dips for this case. So in Dips, what I would do to check whether the block formations I see are real or not is through a kinematic sensitivity. So for instance, for both the wedge sliding and planar sliding failures, I would vary the slope dip direction between the angles of, let's say, 45 to 135. So these dip directions for the slope encompass the different slope sections in my open pit. And what you'll notice is that you do get a peak in the critical percentages between certain slope dip directions. So what does that look like, right? When I did the kinematic sensitivity for both wedge and planar sliding, it's very obvious to me that between the slope dip directions of, let's say, 80 to 115, I get a peak in the critical percentages corresponding to the slope section here and the slope section here. And when compared to rock slope, I see the block formations in this section of the slope and this sections of the slope. So it's good that rock slope and dips are telling similar stories. But by doing the 3D block analysis in rock slope, we can communicate additional information for the hazard analysis. So for example, now I can communicate where on my open pit blocks have formed, what are the factors of safeties associated with these blocks. I can also look at the distribution of my weights and volumes. And for the blocks that are filling, what is the required support pressure as distributed in space, along with the required anchoring length into competent rock, and that you can view through the contours of the block failure depth. So that's the end of example 1. And Julian, are there any questions posted in the chat at this point?
So I'm taking a quick look and don't see any new questions, but I do have a quick question regarding some of the features that you've showed, specifically regarding the DFN that's found in RS3. Is there any plan to link the DFN in RS3 to RocSlope?
Yeah, there is a plan for that. Absolutely. And actually, in my second example, I'll kind of show right now a way to utilize DFN without actually having it implemented in RocSlope. But definitely in the future, we do want to make the processes very easy and preferably to be able to generate DFN directly in RocSlope.
Perfect. And okay. And one last question. You showed the kinematic analysis in Dips. So in Dips, you can also perform a kinematic analysis for toppling failures. Can you do toppling analysis in RocSlope?
Okay, so currently the failure modes considered in RocSlope are sliding, lifting, and falling. 3D toppling is currently in research and development. So the answer is no, not right now, but stay tuned.
Perfect.
Yep.
That's it for me.
Okay. So now let's look at example 2. Okay. My example 2 is for a proposed slope cut. And in this example, I'm really not as data rich. So I have the geometry, the general geometry of the proposed slope cut. It's generally southeast facing, and the overall height is 40 meters, and each cut is 68 degrees. And the field data I have in this case are just a couple of linear traverses. So I don't know the exact location of joints. Now, what I want to do in RocSlope in this example is to basically answer a couple of uncertainties, such as, well, is there a way to populate the joints in my 3D slope geometry? For instance, using some sort of distributions, right? So this is where we can use dips. The second question is, can there be different scales of failures? Can there be crest failures, failures on the walls, or perhaps a larger inter-ram failure that can pass through the multiple slope cuts or benches? Okay. So let's process our linear traverse data first and see what we can do in this case. So here in Dips, you see the grid data view again. And I have 6 linear traverses, and the data formats are dip and dip direction as populated in columns orientation 1 and orientation 2. So just a note here, I also have a column for phi, and this is a value that you may be able to empirically correlate using the JRC or JCS. So then the next step in my data processing would, again, to define sets. And then using the mean set data, I can perform a kinematic assessment. I would also take this opportunity to do a sensitivity analysis now by varying the slope dip directions between 80 degrees to 100. Because if you take a look at our slope, I have a range of slope directions between 80 to 100. So I want to see if there are critical sections, which I can approximate using this kinematic sensitivity analysis. Right. So I can see that perhaps there's an increase in the critical percentages for wedge sliding as I'm moving southward or towards the 90 or 100 degree slope dip direction. Okay. So now going into RocSlope, I mentioned the uncertainties we want to address. And then given the uncertainties, I would like to do a probabilistic analysis. And I'm using 100 simulations. So in each simulation, I will be varying the shear strength of the joints. But I would also like to somehow randomize the joint locations, orientations, and sizes in some way. So this is a case where we don't know the joint locations, but we can use synthetic joints, which requires 3 main components. So the first component is defining the joint shear strength. As you can see here, I have 4 properties corresponding to the 4 joint sets that were defined in Dips. And then for each of these joint strength properties, I have defined some statistics for the phi. So this again is something you can process in Dips. For example, going to analysis chart. If you have a column for the phi, for example, you can plot that to get the distributions for the various sets. So the strength was the first component. The second component is that you need to define a traverse. So here my traverse is highlighted in red. So I'm making an assumption here because I'm assuming that I'm going to populate the joints along this traverse, right? The third component is you need to define the the distributions for the orientation, spacing, and size of the joints. So I'm going to define synthetic joints. And here you see 4 synthetic joint properties defined. Now for the orientation distribution, notice I have fissure and some mean dip, dip direction, and the Fisher-K dispersion coefficient. These values were imported directly from Dips after I have defined the sets. Right? You'll also need entries for the radius and spacing. Again, going back to Dips, I can analyze for the distribution of the joint spacings as found from my linear traverses. And I can do the same for the radius or the observed sizes of the joints. Now to actually place these joints on the slope, I have my traverse, and I'm going to be using this traverse for all 4 of my joint sets. So for convenience, I'm just going to copy these coordinates and reuse them. So now to add the synthetic joints, I would be using the coordinates I have for the traverse. And next would be assigning the synthetic joints along this traverse. So you can see here that the spacing, disk size, and orientation of the joints populated on this traverse are randomized, and they're pulling from the input statistic distributions. And I will repeat this process for all of my joint sets so that the model would actually look something like this. Okay. So by this point, we actually have enough information to compute and to generate some results. So now what can we communicate in terms of the slope hazard? First is that you'll see blocks can actually form in all directions of the slope. However, the more critical blocks, or the ones with the lower minimum factor of safety of all the simulations, are located somewhere here or towards the south, right? So if you recall from the kinematic sensitivity analysis, which I'm trying to find right now, okay, we saw an increase in the critical percentages for wedge sliding as we're going south. So that's good. We're seeing similar results, right? But now in RocSlope, additionally, for probabilistic assessment, we can view not just the minimum factor of safety for the blocks, but also the maximum support pressure as required for each block among all the simulations, the maximum failure depth, and a heat map of the probability of failure to see which part of the slope is more likely to fail. And also, if you're interested in certain blocks, like I would with this one, I can hover over it and then get the block ID, which is 2 in this case. And then I can plot some statistics for this result set. So for instance, cumulative plot, I would like to know not just the max support pressure, but perhaps a percentile design pressure for a single block with ID 2. Okay, so maximum percentile support pressure. Okay. Now, keep in mind that the blocks you are currently viewing are formed from the synthetic joint sets, but each synthetic joint set represents just one realization or one possible realization of the joints as generated based on the input set statistics. Now, if I randomize the synthetic joints, so for instance, I'm going to randomize my synthetic joint set 1. So right now, through the randomization of this joint set, I can vary the joint location, spacing, and size. And thus, if I do this for all of my joint sets, I can vary the location of my blocks as well. So this just means in a probabilistic analysis, the synthetic joints should be randomized multiple times in order to assess the different possibilities of block formation. Now, for the last part of this example, I want to revisit an assumption I made, which was that I placed a traverse, or I placed the synthetic joints on this crest. Right? I placed it on this crest. But I could have placed the joints on this crest up here, or perhaps both of them. So the reality is that joints are going to populate the entire slope and not necessarily just at the crest. So if you have additional information or enough information to characterize a fracture network, then you would not need to make assumptions about the traverse placement like I have done. So as an example, I've generated a discrete fracture network in RS3, which is the Rock Science 3D finite element package. So here I've defined 4 parallel joint sets, and the required parameters are you can now select the shape of the joints or the defect surfaces. You would need length 1 and length 2, because keep in mind that the defects are now on a plane. You would need spacing, persistences 1 and 2 expressed as ratios, and of course the orientations, dip and dip direction. And what I've done is I've exported these joint sets into a common geometry format like a .obj. And then in RocSlope, I can simply import the surfaces, which are geometry files, and then assign joint properties to the surfaces. Okay, so here you see all the surfaces for the joint network in an OBJ file. I'll just bring that in. And then for this set of surfaces, I add joint surface, joint property 1, and so on for all of my joint sets. Right. So now you can see that the joints have populated the entire slope volume. And potentially, now you can get blocks forming not just at the crest, but on other parts of the slope. And here you can see that I can get multiple blocks next to each other forming, and this would be, the DFN will be better for analyzing for key blocks as well. So that concludes my second example and the presentation part.
Can you briefly comment how joint location is defined in RS sheet show the DFN tool?
So let me just exit this end slideshow. Let me just go back to RS3. So what I've done here basically is, if you look at the joint network, basically we have this volume, but you need to place the volume, which means that you need a reference point. And then these joints, each joint set within my network would be generated based on your input statistics for the length, spacing, persistence, etc.
All right, thank you, Chris. Okay, I'll go for one last question. Someone asked, would you provide a reference on how to estimate the strength of the joints?
Yeah, so in our Q&A, which we will email out in 2 weeks, perhaps we can provide some correlations.
Okay. How does RocSlope help in defining the length of anchor to stabilize blocks? Does this require us to define anchors pull-out resistance?
I'm sorry, could you repeat the question again?
Sure. How does RocSlope help in defining the length of anchor to stabilize blocks? Does this require us to define anchors pull-out resistance?
Oh, I see. Okay. So for instance, if I have a model here, RocSlope can provide you with the failure depth, and then the failure depth you would then use to design for the anchor length itself, right? So here the failure depth can be contoured. And if you wanted to, for instance, actually add bolts or an anchor in RocSlope, you can do that by going into, let's say, add bolts. And you would define the pattern of the bolts, the spacing, the pattern angle, offset, and the bolt length is here, right? And when you apply to the slope, you can study the effects on how the factor of safety may have changed. Well, thank you everyone for your attention and taking the time to fill out the polls. I hope you've enjoyed this webinar and found it informative. And please, at any time, if you have any questions or any suggestions for future webinars or perhaps new features you would like to see, please let us know. Thank you very much and have a great day.